Right, well, welcome back to the second half of lecture number 5 for Engineering 101, and we're going to be talking about some of the logical operations that we talked about previously in the first part of this lecture. So we just discussed how to add two binary numbers together in a simple way, but it turns out there is a different way of combining binary numbers, and bear with me, it might not seem super relevant at first, but let's say we had some binary numbers and we want to do an AND operation on them. AND is one of the fundamental logical operations, and it's really just asking a simple question. It's asking you to answer the question, are both inputs A and B true? If that statement is true, then you should return 1, and if it's not true, you should return false. So, for example, here I've got 4 different possible combinations. If our combining numbers are both 0, and we ask that question, are both inputs A and B true? No, that's not true, therefore our logical conclusion, our logical statement is that that's false, and so AND would return false, and the binary equivalent of that is 0. If one was true and the other one was not, so lines 2 and 3 in that table, then we can see that we also get false because both inputs are not true. And then the final one, if A is 1 and B is 1, so if they're both true, then yes, we can finally answer true to that statement, and that's what gives us that true logical output. So all I'm saying is that if we have 0 and 0, and I ask you to AND them together, if it's 0 and 0, the AND of that is 0. The output's still 0, and only if both inputs are true, if this is true, it does. The nice thing about an AND gate is not just some airy-fairy concept, it is actually a physical electronic circuit that we're going to be looking into more later on in Engineering 101. So you can actually see this wired up on paper, and if you do, you'll frequently see it written as this curly gate like this. You'll have seen this in Engineering 121, but it usually has 2 inputs and 1 output, and all we're saying is that this output is only ever 1 if both of those inputs are also 1. That's physically what an AND gate means. And usually when you see it, if it's written down in a logical form, it'll be written as A dot B. That's what the shorthand for AND is. The other really common logical operator is the logical OR, and it asks a similar but subtly different question. It's saying, is either of those inputs true? And if either of them are, return true. If neither of them are, return false. So for OR, if I ask you the same question, we've got 2 inputs. If they're both 0, are either of those inputs true? No. So we return 0. If let's say we make the top one 1, then our OR gate now returns 1, because at least one of them is true. Same as if we flip them up the other way. So, oops, that's what I had before. 0 and 1, that also returns 1. And finally, and this might be a little bit counterintuitive to some of you, if they are both true, this also returns true, just like the AND gate did before. Once again, this isn't just a weird logical quirk, it is a physical electronic gate that can be wired up. When you see it written down, it's written like this kind of slightly more pointy version of the AND gate, so we usually draw it something like this, and with 2 inputs like this. And all we're saying is that this outputs 1 if either of those inputs are 1, or if both of those inputs are 1. If it's written down in logical form, it's written A plus B, as many of you will have seen in Engineering 121. The final logical gate that we're going to talk about today, though, is the exclusive OR. It's very, very similar to OR, and the question it asks is either input true, but not both? So in this case, if we have 0, 0, 0, 1, 1, 0, and 1, 1, so these are our 4 possible combinations. If I draw them out the same way they are on the slide, the logical exclusive OR would return 0 for that, because neither are true, 1 for that, because one of them is, 1 for that, because one of them is true, and 0 for that, because both of them are true. And the exclusive OR essentially is the normal OR missing that one down there. Once again, it can be written out. It's the curly version with another line behind it, and when it's written, it's an normal plus, but with a circle around it to let you know it's the exclusive OR. So, why am I talking about that? Well, if we go back to binary, what we were talking about in part 1 of this lecture, is that what you may have noticed is that the output for our carry and our sum actually match 2 of those logical operations. I've re-put up the combinations of the binary numbers from the carry and sum in the first part on the slide now. And what you can hopefully see is that carry corresponds to the AND operation. It's exactly the same, the logical output is identical, and sum corresponds exactly to the exclusive OR. So what that practically means is, without doing the bitwise binary addition that we did by hand before, just by using the logical operations of AND and exclusive OR, I can tell you what the carry and the sum bits of any binary addition process will be. And so physically that's how computers do it. They don't do this bitwise carry one add it process that we do. They do logical operations instead, and the end result is identical to decimal addition. So, summary, AND gates give us the carry outputs, and exclusive OR gates give us the sum outputs. So the upshot of this is just what I said. We can physically create a device for calculating, for doing binary addition without having any human do it whatsoever. And all this is achieved by is using an exclusive OR and an AND gate wired together. So what you can see on the slide at the moment is called a half adder, and it is, as you might guess, part of a wired up calculator. It's the fundamental block of how computers do addition. And simply by adding more components and more inputs, we can calculate more and more complicated things. We will come back to half adders in Engineering 1 in a few weeks when they're more relevant to what you're doing, but for the moment we will leave it there. And in summary, what you should be able to do is show me the table of an OR, an exclusive OR, or an AND gate, and you should be able to explain why exclusive OR rather than OR is used in binary addition. And if you're looking for a challenge, go and find out how AND gates are physically made. You'll have to understand what things called transistors are, and if you don't worry, we'll cover them in Engineering 110. So we'll finish up there. As I said, those are the summary for you to check when you're going back through these slides. Memorize the AND, OR, and XOR gates, memorize their tables, and memorize what they look like. It will come in very, very handy in a lot of future papers. As a reminder, the evening study groups, they are, this is now correct, they are held Monday and Wednesday in AM106 from 5 o'clock onwards. We push the start time forwards so that people could turn up after the physics labs. So yeah, we will finish it there. Hopefully this lecture has been helpful.